All right, just trying to wrap up a little bit of the 9.4b material. We were talking about that summation notation, that capital sigma, all right, which is telling us we want to add the terms of this series. We decided that this first one here was arithmetic. What was our reason for knowing that? Okay, it's linear in that mx plus b kind of format, right? If you have a linear formula or rule for the sequence, that makes it arithmetic, which means we can use our nice arithmetic formula, right? How did we sum arithmetic series? What was our formula? S sub n equals what? N over 2, okay? Number of terms divided by 2. So we were pairing them up, and each pair added up to what? A sub 1, first term, plus a sub n, the last term. Yes? So if it's arithmetic, by all means, I want you to be using that formula. If we look at our next example, though, we are summing from 1 to 7. Our formula says take n minus 1 quantity squared. Is that mx plus b? No, it's not linear. So it is not arithmetic. If you have one that is not arithmetic, you can't use your arithmetic formula. We don't have a formula for summing a sequence that's not arithmetic or geometric. So what we can do is we can figure out how many terms are we supposed to add. And if we're going from 1 to 7, that's how many numbers? 7 numbers, okay? So let's look at what those 7 numbers are. So 1, 2, 3, 4, 5, 6, 7. We have 7 terms that we're supposed to be adding up. What do we get if we put a 1 in for n? 1 minus 1 is 0. 0 squared is 0. We put a 2 in. 2 minus 1 is 1 squared. Put a 3 in, we get 2 squared. Put a 4 in, we end up with 3 squared. Are you following the pattern? Okay, so 4 squared would be 16. 5 squared would be 25. And 6 squared would be 36. And it's asking me, this sigma notation is asking me to add these all together. So take a minute and add those up. Look for some shortcuts. All right, looking for some shortcuts. What could we do? Okay, we could pair up 36 and 4, that is 40. We could pair up 1 and 9, that's 10. What else? What do we get when we take 16 plus 25? 41 plus another 50, 91 for a total? Okay. The next one, was that arithmetic? Yes, so we did that one in our previous notes. How about the last one here? Arithmetic? No. All right. How many numbers are we adding? If we go from 0 to 100, that's how many numbers? It's 101 numbers. We're supposed to add up 101 numbers, and it's not arithmetic. All right. So what can we do? Let's look and see if there's a pattern. If we have 0, 1, 2, 3, etc., all the way up to 100, right? Those are the terms we're supposed to figure out. What do we get if we put a 0 in? What's negative 1 to the 0 power?
0. 1.
Anything to the 0 power is 1. If we put a 1 in, we've got negative 1 to the first power, which is negative 1. We put in negative 1 to the second power, to the third power, What's happening when I add these all up? 1 plus negative 1 is 0. 1 plus negative 1 is 0. I'm going to have that same pattern all the way through, correct? So my question for you is my last number the end of a pair, so my total is going to be 0, or is it the start of the next pair? What is negative 1 to the 100th power? It's a 1. Yes? So that's the start of the next pair. What's another way I could have known that's the start of the next pair? Okay, so even numbers we're starting, right? 0, 2, 4 would be the start. So 100 is an even number. It's the start of the pair. Yes? Another way of thinking about it, we said we were adding up 101 things, correct? So that 101st, that last number, is the start of another pair. Yes? Okay. So my sum here is what? Just the 1, right? Everything up until this last term, those were always adding up to zeros. And we just have a 1 at the end. We are going to shift to looking at geometric series today. Keep in mind that when you take your test on Friday, we have arithmetic sequences in series, we have geometric sequences in series, and we have some that are neither of those. So just like the 2 examples we did today, if you have a formula that's not fitting our arithmetic or geometric patterns, you can't use them. You have to go back and do it the old-fashioned way, where we write them all down and add them up. Okay? All right, so I'm going to shift to the 9.5a notes. Go ahead and find that in your packet. All right, 9.5a. We are defining what a geometric series is, and we're going to start looking at how we can find its sum. All right, go ahead and grab out your green sheets that you've been writing all your formulas down. We're going to add another one today. All right, it says you can write any whole number that has the same digit in every place as the sum of the terms of a geometric sequence. For example, if we look at the number 4,444, every digit's a 4. If we think of creating a sequence and think of place value, our first 4 in the ones column, we need 4 times 1, but that's 4 times 10 to the 0 power. 10 to the 0 is 1. When we move to the tens place, we need 4 times 10. When we move to the hundreds place, we need 4 times 100, or 10 squared. To get the 4,000, we need 4 times 10 cubed. And so what we're doing is we're taking a 4, and each time to move over one space in our number, we need to multiply in an extra 10. So it's creating a geometric sequence. Our first term is 4. We're multiplying by 10, n minus 1 times. So any number that has repeated digits like that could be created with a geometric sequence. Rational numbers. When you divide 2 numbers and you get that repeating decimal, same idea. So 47 divided by 90 gets us 0.5222. The 5/10 is locked in. We'd have to have that as our first term. But then everything after that, we're just adding another 2. And we just have to make sure we get the place value right. So this 2 is in the hundredths place. That's 1/10 squared. This is in the thousandths place, or 1/10 cubed. And again, it's going to create that pattern. Okay? So we are going to look at geometric sequences, and then we're going to start adding those terms together. In other words, a geometric series. The things that we are going to have to know in order to add them up is, what is the first term? how many terms are we adding, and what is the common ratio. Now, our formula for this looks more complicated, and I'm going to actually have you rewrite it a little bit with some extra parentheses, because most students are able to put the numbers in the right spot on paper, but then they enter it incorrectly on their calculator. So I want to have you make sure you know where the parentheses need to be. So we're going to write S sub n equals our first term times, so we're going to have parentheses, 1 minus. Now I want you to put parentheses around the r, and then it's to the nth power. Then you're going to close off the numerator parenthesis, and in the denominator, you need another set of parentheses around 1 minus r. If you use parentheses like I've just written as you type it in your calculator, you should be fine. All right, I'm going to pause the recording for a minute. I want you to fill this in. You should have 2 boxes on your green sheet in the geometric column that are still empty. This is going to be in the top one. Make sure you put the word finite next to this one. It says, what is the sum of the finite geometric series? If I hadn't told you it was geometric, would you know? Would you be able to look at that and tell? All right, what is it that you're looking for? All right, what is it that we're multiplying by, or that common ratio? 2. All right, so we did 6 divided by 3, 12 divided by 6, right? We got 2 for all of those. So it is our common ratio. In order to come up with our sum, we said there were 3 things that we had to know. We had to know r, we have to know a sub 1, our first term, and we have to know how many numbers we're supposed to be adding. What of those pieces do we know? We already found r. We know the first term is 3, okay? Do we know how many terms we're supposed to be adding up? No. We know we've got 1, 2, 3, 4, but then they've got the little dot, dot, dot. We don't know how many terms are in between there, but we're trying to get out to that last term. So everybody wants to jump to the summation formula because we see all these little plus signs in here. It says we're supposed to add these up. We can't go to that formula quite yet. We need to go back for a second to our geometric a sub n formula, the formula for the nth term. First term times r to the n minus 1 power. We're going to use that to help us figure out how many terms we're adding up. In other words, to help us find n. So you told me that the first term was 3. The r value was 2. We don't know n, but we know that last number is supposed to be 3072. So how can we work backwards to find n? Okay, let's divide the 3 over first. That's a good idea. What's 3072 if we divide by 3? Okay. Now, we have several ways we can figure this out. You could use your power chart. 2 to some power is supposed to be 1024. We could use logs, right? We worked on finding logs already. We could hunt on our calculator. 2 to what power? Just trial and error. Use one of those methods. You need to figure out what 1024 is 2 to what power? That's what we're looking for. All right, regardless of which method you tried, I'm hearing 2 to the 10th equals 2 to the n minus 1. So what would n have to be? N would have to be 11. All right, so we now know the 3 things that we have to fill in our formula. Okay? We're going to go back now to our summation rule. It says take our first term, which was 3, times 1 minus r, which is 2 in this case, to the nth power. And what did we say n was? 11. And we're dividing by 1 minus r. Okay, so we are summing 11 numbers. I want you to prove to me that the answer to this is 6,141. So try it on your calculators. Make sure you're getting that number. If you're not, get your hand up in the air and I'll come check what you're typing in your calculator. All right, our second example here is in that summation notation again. So you see that Greek letter sigma that tells you you're adding these things up. Is it geometric? If it's geometric, remember our pattern for geometric? A sub 1 times r to the n minus 1. Okay, does it look something like that? Yeah. It's off a little bit. They have an n instead of an n minus 1. But the key for something to be geometric is your variable is your power. So just like with arithmetic ones, we were looking for something that was linear. Geometric ones, we're looking for something that's exponential. All right, where your exponent is the power. So this is a geometric pattern. And if you are taking the test and you're not sure, could you generate the first few numbers in the list and see what it's looking like? Yeah. All right. The three things we need. First term, r and n. Let's start with n. How many numbers are we adding up? If we're going from 0 to 20, how many numbers is that? It's 21 numbers, right? All right. Do we know what r is? R is that common ratio, right? The thing that we're multiplying by over and over again. So what is being raised to the power that says we're multiplying these up? The 1/2. Okay. Now, I wrote down a sub 1 because in our formula we refer to that as our first term. But in this case, the first term is what we get when we substitute in a 0. Yes? So put a 0 in here. What happens? What's 1/2 to the 0? And 1 times 4 is 4. So the first term in my list would be a 4. All right, go ahead and fill in those numbers into your big summation formula. We're summing 21 numbers. Fill in your formula and go ahead and put it in your calculator. All right, so first term was 4 times 1 minus 1/2 to the 21st power, all over 1 minus 1/2. And it came out to be what? About 8. It was 7.99 something, right? So our sum is about 8. Okay. Is the next one geometric? How do we know? There's a common ratio. What is our common ratio on this one? -2. That's what we are multiplying by. So r is -2. It means it's geometric. A sub 1 is -15. How about n? Yeah, I gave you a pretty short little series here, right? We can just count the numbers. There's no little dot, dot, dot in between them. All right, so there are 6 numbers in that list. If it is geometric, I expect you to use the formula. I do not want you grabbing your calculator and just typing in -15 plus 30 minus 60 plus 120. All right, I want you to use the formula. So summing 6 numbers, our first term was -15 times 1 minus our r value to the 6th power, all divided by 1 minus r. This question is why you need parentheses around r. When r is a positive number, It's not a big deal. If you forget to put the parentheses around it, it's not going to affect your answer. But when r is negative, it matters. Because right here, I'm taking a negative number to a power. And if that power is positive, or sorry, if that power is even, it's going to turn it into a positive value. And if it's odd, it's going to leave it negative. So go ahead with your calculators. Prove to me the answer should be 315. I want you to type it in and make sure that works. All right, our next question here. One sec. All right, I did not include the whole story in your notes, so you'll have to just listen here. It says a famous story involves a soldier who rescues his king in battle. The king grants him any prize within reason from the riches of the kingdom. The soldier asks for a chessboard with a single kernel of wheat on the first square, 2 kernels of wheat on the second square, then 4, then 8, and so on, for all 64 squares of the chessboard. The king decides that the request is reasonable. So according to the story, how many total kernels of wheat did the soldier request? Is this geometric?
Yes.
All right. So you know the things that we have to know for our formula. Go ahead and talk as your groups. How many kernels of wheat did he want? All right. So of the things that we need, first term is 1. R is 2. N is 64. So you summed all 64 little squares of the chessboard. First term times 1 minus r to the 64th power over 1 minus r. Okay. And you ended up with what? 1.845 times 10 to the 19th. What label would we put on this? Okay, so the soldier is really asking for a total of 1.845 times 10 to the 19th kernels of wheat. Okay? Is that a lot? All right. We're going to put it into a different context. It says a bushel of wheat contains about 1 million kernels. The total U.S. output of wheat in a recent year was just over 2.1 billion bushels. How many years of production at that level would it take the United States to produce enough wheat to satisfy the soldier's reasonable request? So, first of all, 1 million is a 1 with how many zeros? 6. So could we write that as 1 times 10 to the 6th? Is that the same thing? So what we want to do is we want to take this 1.845 times 10 to the 19th bushels, kernels, and we're going to divide it by 1 times 10 to the 6th. That's how many kernels per bushel, right? Kernels per bushel. So this will get us how many bushels of wheat we're looking at. Well, 1.845 divided by 1 is just 1.845. What is 10 to the 19th divided by 10 to the 6th? Good. So we have 1.845 times 10 to the 13th bushels. Okay? Now it says that the United States can produce 2.1 billion bushels every year. 2.1 billion would be 2.1 times 10 to what power? A billion has 9 zeros? So times 10 to the 9th? So let's take how many bushels the soldier wanted and divide it by how many bushels per year we can do? 2.1 times 10 to the 9th. That's bushels per year. So what are we going to end up with for a label on this answer? Years. We're trying to figure out how many years it'll take us, right? Again, dividing scientific notation. Divide the front numbers and do what with our powers? Subtract. So grab your calculators. What's 1.845 divided by 2.1? 0.8. Okay. And it's times 10 to the 4th. So 10 to the 4th means our decimal's moving 4 places to the right. So if we move our decimal, we'd have 8,786 years. It would take the United States. We make quite a bit of wheat, yes, compared to some countries. It would take us almost 8,800 years to make that much wheat. And the king thought it was a reasonable request, right? 1 kernel, 2 kernels, 4 kernels. Doesn't seem like a lot. But you're doubling it 64 times, right? And then you're adding all those numbers together. So it's not just how many were on the 64th square. It's if you add all the squares together, how many would you have? And it would take us almost 8,800 years. Okay? So, not a reasonable request. A similar question. You go home and you tell your parents, I will do the dishes every day for a month. And here's what I want you to pay me. A penny on the first day, 2 pennies on the second day, 4 pennies on the third day. Just double my money each day. All right? I want you guys to figure out how many you'd have after 30 days. What would the total amount of money your parents have paid you to do the dishes? Okay? Now, homework today. We did a little bit. We finished up 9.4b. So you have a few questions from 9.4. Then you have the first part of 9.5a that I want you to do. If you did not do the formative quiz, 9.1 to 9.3 yet, you need to do that. All right? And then I do want you to try the penny allowance thing, all right, with doing the dishes. Or if you want to find a different chore to tell your parents you'll do, that's fine. See if they would agree to it. And then explain to them how much money they are really going to be paying you. Or wait a month and then tell them. All right. Questions? You're doing both. They're both short, but it's on 2 separate pages. Okay?